Hi, and welcome to 9.1 Momentum and Impulse Introduction. We're going to talk about momentum and impulse today. Impulse is just a change in momentum, so don't get confused by this term impulse. If an object has some kind of momentum, and then maybe a force is exerted on that object, changing its momentum, then now it has a new momentum. The change in the momentum is equal to the impulse, which we use a J to represent. So that's just that's as far as we get with impulse. We don't really talk about J is equal to Ft in this assignment. That's for 9.2, but just the idea that impulse is a change in momentum. So number 1 says complete the table below. The first row has been completed for you as an example. So for acceleration, we use an A, and the units are meters per second squared. For mass, we use an M, and we use kilograms. For velocity, this is a V, and you know it's a meter per second. The reason that we're doing this is just because it's a kind of weird. We use a P to represent momentum, and the units for momentum are kilogram meters per second. And here's why. The formula for momentum is equal to the mass times the velocity. So the units for mass are kilograms and velocity are meters per second. So it makes sense that for momentum it would be a kilogram times a meter per second. All right, that's where it comes from. For impulse, it's a J. They use a J to represent the impulse. And actually you could put two things for the units for impulse. Since impulse is just a change in the momentum, if you had maybe your initial momentum was 5 kilogram meters per second, and now your final momentum is 4 kilogram meters per second, your change in momentum in this case would be 1 kilogram meter per second. So you could definitely put a kilogram meter per second as well. Again, it's just the change. How much did your momentum change by? It changed by this many kilogram meters per second. Alternatively, and we'll talk about this more in the next homework, you could also use units of a Newton times a second, a Newton second. You don't necessarily have to put the dot, but so you could do like this or that. Okay, is velocity a vector or a scalar? Remember, vector has magnitude plus direction, and a scalar is only magnitude. And a velocity is a vector that has, maybe you're going 5 meters per second. This looks like 45 degrees north of east. Here's your direction part, and you could tell it's a vector because we're representing the velocity with an arrow, as opposed to just saying the speed. I'm moving at 5 meters per second at a rate of 5 meters every second. So velocity is a vector. You should know that this is like kind of just review. You could skip ahead in the video if you know all this stuff, obviously. Number 3, a velocity of negative 4.5 meters per second indicates that an object is traveling to the left. By convention, anytime we use a negative sign, we say to the left, or maybe it's going down, maybe it's going west, maybe it's going south. It's the negative direction, so it would be left. So keep it like that. 4, give an example of a velocity of an object traveling to the right. It could be any positive number with the units of meters per second. So maybe it's positive 4.5 meters per second, or any positive number meters per second. Doesn't matter. Number 5, mass is blank related to momentum. 6 is velocity is blank related to momentum. So this is saying, okay, we're looking for a relationship type of problem. Anytime you're relating two variables together in a problem like this, you want to find the equation that relates the variables. So now they're talking about momentum and mass. We know the equation is P for momentum is equal to mass times the velocity. And as you can see from the equation, this is a direct relationship. Some people have been asking me, what's the difference between direct, inverse, and exponential? Or is it not related to momentum at all? We'll do this one again. So 6, velocity is also directly related. All right, you could see from the relationship there. Just as an aside, if you're wondering about the different types of relationships, let's talk about them quickly. In physics, we talk about a direct relationship. We talk about an inverse, and we talk about an exponential. For direct relationship, the basic form is y is equal to x, and the graph looks like a straight line. So we said that momentum was direct relationship because P is equal to mv. The x and the y are on the same side. They're like in the numerator, you could say, and the x isn't being squared at all. So whatever that mass is, it's directly related to the momentum. If you double the mass, the momentum doubles. If you triple the mass, the momentum triples. It's directly related. For inverse, that's the one where it's y is equal to 1 over x, and the graph looks like this. An example of this would be maybe Newton's second law. The acceleration is directly proportional to the net force. So that's a direct relationship, but it's inversely related to the mass. So as you double the mass of an object, it won't accelerate it as much. It'll be 1/2 as great. If you double the mass, the acceleration becomes 1/2 as great. So anytime you see an equation where there's something in the denominator, those two variables are inversely related. And for exponential, you probably know what it looks like. Y is equal to x squared. The graph would look like half a parabola. And an example of this might be kinetic energy is equal to 1/2 mv squared. Now again, for kinetic energy, mass is directly related to kinetic energy, but as you can see, because of the exponent, velocity is exponentially related to the kinetic energy. So if you double the velocity of an object, the kinetic energy will increase exponentially. It not only doubles, it 2 squared. It's 4 times as great. So if you double the velocity, you get 4 times as much kinetic energy because of this exponential relationship. Okay, back to the homework. So that's how we knew for 5 and 6 that mass is directly related to momentum as well as velocity. They're both directly related. Okay, good. So 7, mass has a blank effect as velocity when it pertains to momentum. That's kind of like a weirdly worded multiple choice question. What I was trying to get at here was it has the same effect. If you double the velocity, the momentum doubles. If you double the mass, the momentum also doubles. As opposed to like we used kinetic energy, so the KE is equal to 1/2 mv squared. In this case, the velocity has a greater effect on the kinetic energy because if you double the velocity, it multiplies it by 4. If you triple the velocity, it multiplies it by 9. Whereas if you double the mass, the kinetic energy only doubles. And if you triple the mass, the kinetic energy triples. So as you can see from the equation, the velocity would affect the kinetic energy more. But since these are both directly related, they have equal effect when it comes to momentum. That's what I was trying to get at there. Okay, number 8 says organize the objects from least to greatest momentum. So you had to calculate P equals mv. The momentum is the mass times the velocity for each of these things. For A, it's super ambiguous. They don't tell you what's the mass. I don't know, and they don't tell you like a number for the velocity like in the other ones, but do you know what the velocity of a train at rest is? The velocity is equal to 0 meters per second. So you could use your equation here. P is equal to m times 0 meters per second, and you can see that the momentum is equal to 0 kilogram meters per second. Doesn't matter what the train's mass is. If you're not moving, you don't have any momentum. So A is first. It's the least greatest, the train. Okay, let me erase some of this stuff. Now we have B is a 2,000 kilogram car traveling at 4 meters per second. So you get a momentum of 8,000 kilogram meters per second. So this is 8,000. Then you have a 2-gram B flying at 10 meters per second. Now this is 2 grams, so it's even less kilograms. 0.123. Oh no, 2. But it's 3 decimal places for kilo. So you got 0.002 times 10. You get 0.02 kilogram meters per second. Not very much momentum at all, especially compared to the momentum of a car. We're talking about a B here. All right, so now we have a 2-kilogram Falcon flying at 40 meters per second. So it has a momentum of 80 kilogram meters per second. So we knew that the train was going to be the least because it didn't have any momentum. The second least amount of momentum would be for the B, which was choice C. The third least, or the second most momentum, would be D, which is the Falcon. And then the most momentum is the car. So you should get A, C, D, B, like that. Very good. Number 9, if an object collides with another object, what do you think happens to its momentum? Oh, this is kind of like a teaser. After we talk about impulse and momentum, we talk about the conservation of momentum. So momentum is conserved, just like how energy is conserved. The total energy on top of a roller coaster on top of a hill, it has some potential energy. It's in the system. The total energy remains the same as it goes down the hill. It just transfers from potential to kinetic. But if at any point, if you add the total energy together, the potential plus the kinetic, you'd get the same amount of total energy as before. And it's the same with momentum. So actually, the total momentum for the system is going to stay the same, but it could transfer from one object to another. Let's say you have a ball and it has some momentum, but then it collides into another ball that's at rest. So this is like the initial situation. In the final situation, so the ball's coming along, boom, it hits the other ball. Maybe ball 1 it then comes to a rest. You ever see that before on like a pool hall? This one comes to a rest and the second one goes off with some momentum. Well, if this is now 0, then this momentum has to be equal to that momentum. That's like the most basic version of the law of conservation of momentum. It's just the total energy gets transferred from one to the other because there's at least one that's at rest. Anyway, what you could say is, if an object collides with another object, what do you think happens to its momentum? Maybe you could say its momentum changes. Maybe you could say it transfers. Hopefully you spell it right, though, with just one R. Yeah, so momentum transfers from one object to the other. Very good. Okay, and then we have the change in momentum is called, anytime an object changes momentum, actually in like our previous example, this object changed its momentum. It had some momentum, now it doesn't have any momentum. So an impulse was exerted by ball 2. It ran into ball 2. There was an equal and opposite force happening there over some impact time. So there was an impulse that acted on the ball, on ball 1, causing its momentum to decrease. Okay, so 1 through 10 were all kind of conceptual. For 8, you had to calculate some stuff, but you could have just looked at the numbers and really kind of figured it out, which one had more momentum. 11 through 19, a lot of calculations, so let's get to it here. It says a toy train has a mass of 2 kilograms, and it's moving to the right, so that means its velocity is positive at 2 meters per second. It says, what is its momentum? So P is equal to mv. Momentum is equal to 2 times 2. So momentum is equal to 4 kilogram meters per second. Number 12. A remote control car of 4 grams, so the mass is 4 grams, kilograms, is moving left at 2 meters per second. So the velocity is 2 meters per second to the left negative. What is the momentum? P is equal to mv. P is equal to 4 times negative 2. So the momentum is equal to negative 8 kilogram meters per second, showing that it's moving to the left. That's why it's negative. Okay, number 13. Car A has a mass. So mass of A is equal to 2,000 kilograms and is traveling to the right at 30 meters per second. So the velocity of A is positive 30 meters per second. It says car B. So now we have a different car. Car B has a mass of 2,500 kilograms, so it's more massive, and it's traveling to the right at 25 meters per second. So more mass, but less velocity. Which car has a greater momentum? Show how you arrived at your answer. So it's just P is equal to mv, but the momentum of car A, we could be specific and continue using our subscripts. And then you have P, the momentum of car B, is equal to the mass of B times the velocity of B. So you plug in your numbers, and then you solve. And as you can see, car B is going to have more momentum. You can put like a greater than sign like that. Okay, number 14, a dump truck has a momentum. So now they're telling you what the momentum is. It's 3.6 times 10 to the 5th kilogram meters per second, and it has a velocity of 15 meters per second. It says, what is the mass of the truck? So we're still doing the guess method, as you can see. It's a good habit to get into, especially when we do those conservation of momentum problems. The conservation problems are going to have a lot of subscripts like that, and it's important to keep yourself organized by doing the guess method. It makes it a lot easier. Trust me, take the time to write it out. All right, get into good habits. All right, so this is 3.6 times 10 to the 5th is equal to the mass times 15. So the mass is equal to 24,000 kilograms. Or it's pretty massive, but it's a dump truck. Maybe it's fully loaded with a bunch of garbage. Okay, I mean, listen, I know it's just multiplying and dividing at this point. You know, the formula is pretty straightforward at this point in the year. You guys are used to using formulas. But again, using the guess method, and just take the little extra time to write it out. Unless you're really crunched for time. Maybe you're doing it on the bus ride over to school or something like that. Number 15, a bullet has a momentum of 12 kilogram meters per second and a mass of 0.05 kilograms. It says, what is the velocity? So it's like the one above where they tell you what the momentum is. So this is 12. The mass is 0.05. And you're looking for the velocity of the bullet. Should be pretty fast. Let's see what it is. 240 meters per second. Yeah, that's pretty fast. That's a good bullet right there. Number 16, a dog has a mass of 20 kilograms, while a cat has a mass. So this is MD, this is MC. The cat is 5 kilograms. And it says if the dog is traveling, so the velocity of the dog is 2 meters per second, how fast must the cat be moving in order to have the same momentum? So you're looking for the velocity of the cat, and they have the same momentum. So you could kind of write yourself a little equation here. The momentum of the dog should be equal to the momentum of the cat. If you wanted to do it in one step, this is an equation that you could use. You're taking the information from the problem and making a useful equation out of it. They said the dog should have the same momentum as the cat, so you just set them equal to each other. And now you can plug in m of the dog, mass of the dog, velocity of the dog is equal to the mass of the cat times the velocity of the cat. And as you can see, we have 3 knowns and 1 unknown, which fits our equation. So you plug in what you know. Now you have 20 times 2 is 40. 40 divided by 5 is 8. So the velocity of the cat must be 8 meters per second, which is more than the dog. But look, the cat is a lot less massive than the dog. So the cat has to go a lot faster than the dog does in order to have the same momentum. Now, there's another way you could do this. Instead of like coming up with your own equation here, kind of, you could just solve. You could say, what is the momentum of the dog? And now, knowing the momentum of the dog, you could figure out what the velocity of the cat should be in order to have the same momentum. So you just plug in the momentum of the dog it should be the momentum of the cat. So you plug in a 40 over here. And then you get to the same answer. The cat has to move at 8 meters per second. 40 divided by 5. Okay, number 17. The dog and the cat in problem 16 are now both moving at different velocities. Give another combination of velocities in which the dog and the cat would have the same momentum. For this problem, I mean, you could feel free to kind of do trial and error and mess around and look at the equation and try different numbers. But what I find is looking at something like this is helpful. You want the momentums to be the same. So we write the same equation. And now we plug in the masses of the dog and the cat. So the dog has to have a mass of 20. It doesn't say we're changing the mass of the dog. We're just changing the velocity of the dog. And the cat has to have a mass of 5, but we could change the velocity of the cat. So now what you could actually do is you could make a relationship to actually make your own equation to solve for the velocity. Let me show you what I mean. I'm going to shift this guy up and erase the top. Okay, so this is the equation that we came up with from this guy. All right, and now let's solve for one of the velocities. What you could do is divide by 5 on both sides. And what you get is the velocity of the cat is equal to 20 divided by 5, 4 times as much as the velocity of the dog. So that's what the relationship is between the cat and the dog. As you could see, the velocity of the dog is 2. The velocity of the cat is 8. So if we tried to plug in our, the velocity of the dog was 2. So 4 times 2, the velocity of the cat is 8. And we just proved that the equation we just made works. So you could check your numbers and see if what you found worked. For example, let's say we don't want to do 2 and 8. Let's say we have like some super dog and super cat. Maybe the dog's going 55 miles an hour. Maybe the dog is going 25 meters per second. So the cat would have to be going 100 meters per second in order to have the same momentum as the dog at 25 meters per second. Plug in what you have. If you plug in your velocity for the dog, it should be 4 times as much as the velocity of the cat. It could be any number. All right. 16 says a 2,000 kilogram car traveling west, so the mass is 2,000 kilograms, and it's traveling west in a straight line on a highway, decreases its speed from 30 meters per second to 23 meters per second in 2 seconds. Okay, so the initial velocity is 30 meters per second, but you're going west, so you better make that negative, right? And then the final velocity is negative 23 meters per second. And the time is 2 seconds. So far, we haven't done any work. We're just writing down the given information. Now it says, what is the impulse imparted by the brakes of the car? Hint, what is the change in momentum? So if it's asking for the impulse, it's asking for the change in the momentum. So you could do this in 2 different ways. So they're looking for J. This is the first way is the way I would do it, because I'm lazy and I don't want to do multiple steps. I want to try to find an equation that I could use for just one step. Now in class we talked about how the impulse was equal to the change in the momentum, and 9 times out of 10 something's momentum is changing because its velocity changes. So the mass is staying the same It's just that you have a change in the velocity. So this is the impulse momentum theorem as far as we know right now. We're going to add in another piece for the next homework assignment, big piece there. But for now, we're just talking about how impulse is a change in the momentum. So they're asking for the impulse. So let me back up. You have an equation with two equal signs. There's three different parts. You want to just use two of those parts. You got to pick out the two useful parts so that you could make your own equation. So they're asking for the impulse. So you better believe the first part is the J. We're going to use this guy. Now, you have a choice. Do I want to do this or do I want to do this? Well, if we're looking at the change in the momentum one, that's PF and PI, the final momentum and the initial, I don't have PF or PI. So that's going to be pretty tough to use in one step. However, if we look at this guy, I have the mass and I have the final velocity and the initial velocity. So that is the next piece of the puzzle that I'm going to use. I'm using this modified version of the impulse momentum theorem by saying the impulse is equal to the mass times the final velocity minus the initial velocity. So that's the equation that we're going to use. Now that we know the givens and the unknown and we have an equation, the next step is to just substitute. See how the guess method kind of helps us here? So we're substituting in 2,000 kilograms. It's always VF minus VI in that order. So the final velocity is negative 23. So this is where the second trick comes into play. You had to make sure that you made it negative because it's west, so don't drop the negative. It's negative 23 minus the initial velocity is negative 30. So this turns into like a plus positive. You could think of it like that. So you get a change in velocity of 7 meters per second. 7 meters per second times 2,000 is going to give you 14,000 kilogram meters per second. Or you could write 14,000 Newton seconds. Both units are fine. We'll keep it like that for now because as far as we know, impulse is just a change in momentum. So it changed by this much momentums, kilogram meters per second. Okay. Now I told you there was a second way to do it. I'm going to do it now. Feel free to skip to 19 if you don't want to watch the second way. But the hint tells you that you should find the change in the momentum. So what you could do is find the initial momentum first. Then you could find the final momentum. And then you could find the change in the momentum. So the initial momentum is equal to the mass times the initial velocity. The final momentum is the mass times the final velocity. And the change is the final momentum minus the initial momentum. So it's like 3 steps instead of just one, which is why I prefer to just use this. But this way is fine too. So you substitute in for both equations. And you get an initial momentum of negative 60,000 kilogram meters per second. And you get a final momentum of negative 46,000. Now, obviously, I kind of did it both at the same time. You could have just done one and then the other. That's fine too. Then you plug in over here. Careful of your negative sign. So the final is negative 46,000 minus negative 60,000. So the change in the momentum, and don't drop any negative signs, you still get the same answer. It's 14,000 kilogram meters per second. And that's equal to the impulse. So you don't even have to put the delta P. You could just put the J. So erase this. And that's the impulse. By definition, it's the change in the momentum. All right, so 2 different ways to do that. Let's do 19. All right, so now we're working on number 19. All right, a lot of my students had questions on this one, so hopefully they just skipped right ahead to 19. It says a 10 kilogram block sliding to the east across a horizontal frictionless surface with a momentum of 50 kilogram meters per second strikes an obstacle. The obstacle exerts an impulse of 20 Newton seconds to the west on the block. What is the momentum of the block after the collision? Okay, Well, if you don't write down the given information and the unknown information and then try to find an equation to help you substitute and solve, this might be tough. And, you know, this is the 19th question. You probably did the homework and you were tired and you didn't feel like doing the guess method and you're like, physics this, I'm done. Let me just show Mr. Nangle that I didn't get it and yell at him for not making a video about it. Well, here's the video. Just write down the guess method. Try writing the guess method yourself and see if you could do it. So the mass is 10 kilograms. Now that you're nice and refreshed. And it's on a frictionless surface with a momentum of 50 kilogram meters per second. So the momentum is 50 kilogram meters per second. But then it strikes an obstacle. And its momentum is going to change because an impulse was exerted on it. So we could call this the initial momentum. Now it's traveling east, so this is positive, that's good. But the impulse exerted is traveling to the west, and it's 20 Newton seconds. So this is negative 20 Newton seconds. You might have seen those units and been confused too. You could have wrote negative 20 kilogram meters per second, and you would not be marked incorrect. Those two units, Newton seconds and kilogram meters per second, they're equivalent to each other. So if you're confused by that, please do not be confused. So it says, what is the momentum of the block after the collision? And you have three variables here. And you might have wanted to do, okay, P is equal to mv, but I don't know what the velocity is. There's no velocity. All right. Well, let's look at what the unknown is. The unknown is pf. Okay. It would be nice to know, so this is your initial, this is your final. It'd be nice to know what the difference between these two are so that we could figure it out. Oh, wait a second. The impulse is the difference. It's the change in the momentum. Let me show you what I'm talking about here. Okay, so the impulse momentum theorem, as we had it, was the change in the momentum is equal to the impulse. And we even tacked on this guy, m delta v, meaning that when you change your momentum, it's because you're changing your velocity. 9 times out of 10, you're not changing your mass. Sometimes you are, though. Now, we have this long equation with 3 different things. One of them is unnecessary, so let's pick out the one. Let's pick out the 2 things that we want to use. They told us what the impulse was, so let's use the impulse. Okay. Now, they're looking for the final momentum. Which piece do you think the final momentum is going to be in? Should we use this piece to find the final momentum or this piece? Hopefully you could tell this guy is not as useful as this guy in terms of finding the final momentum. So we're going to use delta P just like that. So the impulse is equal to the change in the momentum. So that means that the impulse is equal to the final momentum minus the initial momentum. And as you could see, all right, we have the J, we have PI, and we're looking for PF. So this is a good equation to use. Let's use this guy. Now, the only thing you have to be careful on now is making sure that this is negative 20 because the impulse is imparted to the west, and the final momentum is what we're looking for, and the initial momentum was positive 50. So now you solve. The final momentum is going to be positive 30 kilogram meters per second. Now, that's all well and good, but let's kind of figure out what really is going on. You got this impulse acting to the west. What's going on here? So let's start from the beginning. It says a 10 kilogram block is, is sliding east with an initial momentum of 50 kilogram meters per second. And it's on a frictionless surface, and then it strikes an obstacle. So you have this little obstacle here, and it imparts a 20 Newton second impulse west. So now you have an impulse acting west of 20 Newton seconds. Okay, so you're coming in at 50. And then this guy's like, nope, I'm going to change your momentum by 20 in the other direction. So I'm going to decrease your momentum by 20. And then after the collision, you have a final momentum of 50 minus 20, 30 kilogram meters per second. And if you think of it conceptually like that, hopefully it kind of makes more sense now. You have these weird terms, impulse and a unit of Newton seconds, but really you have 50 kilogram meters per second. Basically, let me take the units out of it. You have 50, you subtract 20, you're left over with 30. That's what it comes down to. You change your momentum by 20 kilogram meters per second because this impulse acts in the opposite direction. Now, if we wanted to be really precise, actually, I should have made my diagram, the arrow is a little bit less. All right, so you had a larger arrow here. Now you have less momentum, so the vector should be a little bit smaller because this impulse was acting on the block. Now it says, what is the speed of the block after the collision? Really tough to do if you didn't know what the final momentum is. So now let's use this final momentum. So the momentum is 30 kilogram meters per second after the collision. And we're looking for the velocity after the collision. And we know the mass is the same, 10 kilograms. And it works out to be just the same. P is equal to mv. All right, so this is 30. The mass is 10. The velocity is what we're looking for. So the velocity is equal to 3 meters per second. All right, let's keep this momentum going in 9.2. Have a good day.